Hi kids, like in this class we'll be doing something about gravitation chapter. So basically it is 2D motion. 2D motion we'll be trying to visualize like yeah, in some areas how can we visualize it as 1D motion. So before going to this, let me talk about 1D motion. Like if a particle is moving along x-axis and if you know potential energy as a function of x and kinetic energy as a function of x, you can predict its motion. So that's what you will be doing in SHM also. So similarly we will be trying to do something here. So before going into, let me talk about elliptical motion which will be happening. So if there is sun and some planet will be performing elliptical motion around the sun. So it will be having velocity tangential to whatever the path. Now if I resolve this velocity, I will be having one velocity component along the radius vector, along the position vector, and one perpendicular. That you can see from here also. Position vector velocity will be given by, velocity vector will be given by rate of change of position vector. Position vector can change in magnitude as well as direction. So this is along this direction. So this magnitude is going to be dr by dt or r dash, and this magnitude is going to be omega bar cross r bar, right? So total energy, now this is conservative force which you will be learning in gravitation chapter anyway. So total energy is potential energy plus kinetic energy. This kinetic energy is half m into total velocity square. Total velocity square is this velocity square plus this velocity square. So when I replace it, I will be getting this thing. So when I expand it, I will be getting 3 terms. I will be getting 3 terms. Now this is Vr is dr by dt and V theta is omega cross r. Anyway, we won't be writing this thing. We will be slightly deviating from here because we know it is central force. So conservation of angular momentum will happen. So what is the angular momentum here? It is r into m V theta. R into m V theta. So instead of V theta, when I substitute it back, I will be getting this thing. Now from here to here, when you notice, angular momentum is constant. So this is constant, this is constant, this is constant. So this is the function of r. Now potential energy in case of gravitation, potential energy in case of gravitation will be this much. This is the function of r, this is the function of r, and this is r dash dr by dt. See, dr bar by dt and dr by dt both are different. Dr by dt is differentiation of a magnitude. Okay, so this one I can write it this way. Now this looks like it has 3 terms, like potential energy thing, like this kinetic energy thing has like some 2 different components. But if you bring it here and if you club these 2 terms together, it looks like function of r, only a function of r, only a function of r. Remaining things are constants. Note that angular momentum is constant because it is a central force. It looks like some potential energy term plus kinetic energy term, but in one dimension because it is only magnitude, right? So if I talk about particle moving along x-axis where the distance is measured as r, then this is going to be velocity along that x-axis and this is going to be some kind of potential energy thing. So yeah, so if I call this as some kind of potential energy for one dimension motion and this as kinetic energy for one dimension motion, I can say this problem looks like solving one dimension motion problem, right? So what was that we have done? We have taken total energy, we have expanded it, but one part of kinetic energy we are writing in terms of angular momentum, and as angular momentum is conserved, we can see it like some one dimension problem where we have this much potential energy and this much kinetic energy. Yeah, you can look at this question. We'll solve it according to what we have done till now. For what values of n are circular orbits stable with potential energy minus a by r power n, where a is greater than 0? A is greater than 0 and n is also greater than 0. I mean, that makes sense. Yeah, anyway, we can do it for other a also, but let me go with a greater than 0. So again, we will be going with the same thing as it is a central force, angular momentum will be conserved. So I can write the total energy in this format, where this was given in the question, Now I will be grouping these 2 terms together and I will be calling this as some kind of new potential energy for one dimension problem, and this is kinetic energy for one dimension problem. Potential energy for one dimension problem and kinetic energy for one dimension problem. Now you can see this motion looks like particle moving along one axis where the distance is r. Now we need to see where it is in equilibrium, which is stable equilibrium. Now potential energy effectively is this much for one dimension problem. So its first differentiation is going to be this much. Wherever its first differentiation is going to become 0, that is going to be equilibrium situation. So that equilibrium situation I am calling it as r naught. First differentiation, it will become 0 at r naught. So when I substitute, I will be getting r naught is this much. That is force is going to become 0 yeah, for a given angular momentum we have been treating constant. For a given angular momentum, it will be in stable equilibrium at this particular location of r0. Now I need to see, they are talking about stability, so second differentiation has to be greater than 0. I will be differentiating this one again, that is going to be second differentiation. Second differentiation has to be greater than 0, then potential energy will be minimum. Potential energy will be minimum, that is stable, yeah, stable orbit, right? Now where we have to check? We have to check at this equilibrium position at r0. So when I substitute r0 for this guy and this guy, it will turn out to be this thing, but this entire thing has to be greater than 0 for it to be stable orbit. Stable orbit. So when you manipulate, you will be getting this thing, but yeah, this is nothing but 1 by this thing, 1 by this thing. So when I substitute 1 by this value here, all other stuff will be getting cancelled and I will be getting some kind of inequality, which will happen when n is less than 2. N is less than 2. N is less than 2. So for n is less than 2, in case of potential energy is of this form, if potential energy is of this form where n is less than 2. Now generally in case of gravitation, this r is 1 minus gmm by r power 1, r power 1. So that is going to be stable. So when the force is of the nature 1 by r square, potential energy will be of the format 1 by r minus 1 by r, it will be stable. So when n is less than 2, it will be stable. When n equals to 2, it will be like neutral equilibrium, that we will see later. So for our inversely proportional to r square nature, it is going to be stable. Now based on that, we will be solving this thing. A planet of mass m is currently undergoing a circular orbit about a sun of mass m at radius r0. If the planet is somehow given a slight radial displacement, so something is performing circular motion around the sun, that planet is given slight radial displacement, then what will happen? So yeah, anyway they said it will perform oscillation, determine its angular frequency in the radial direction, what is the resultant trajectory of the planet. Now again we will be doing the same thing. Now we are disturbing it along the radial direction, it was going this way, we are disturbing it along the radial direction. That is not going to change the angular momentum about the sun, because the force when you extend it, it will be passing through the sun. So angular momentum is still remaining same, angular momentum is still remaining same. So this term is going to be, yeah, this cell is going to be remaining same. Now we are disturbing this r, so again we will be doing the same thing. Yeah, total energy we will be writing it as this way, that where this is effective potential. Now we can see it as a one dimension problem where potential energy is this much. Now I need to see where it was in equilibrium in the first place, that is first differentiation of this thing should be equals to 0. That will happen at this particular r0, for a given angular momentum, Now I need to slightly disturb it and see force is acting in which direction. So if u dash is this much, then force is going to be negative of this in r cap direction. So this is the force, but I need to see what will happen if I disturb. Now equilibrium position is somewhere at r0 according to this one dimension figure. So if I disturb it slightly, what is the force acting? So I need to find what is the force at r0 plus delta. So I will substitute r0 plus delta, then I will be using binomial expansion. But note that these two terms were magnitude wise same from here. From here this term and this term are same. Yeah. So one thing will be getting cancelled, the other one, yeah, you can do the mathematical calculation. You will end up getting net force is this much, where small displacement is delta. Now force is mass times of acceleration is displacement's double differentiation, right? You can see it as SHM form, x double dash equals to minus omega square x, so omega will be this much, so time period will be this much. Now if you notice this one, this was the same time period of the planet which was rotating at a distance r0. Now what we have seen is, we have seen at a distance for a given angular momentum r0 is the equilibrium situation, so it will be performing circular motion in that 2D motion. It was performing circular motion. Now with time period this much. Now when you disturb it, by the time it comes back, it will be performing one SHM along the radial direction. The other way of saying it is, if it was performing circular motion, when you disturb it this way, by the time it performs half rotation, it will be going out. Yeah. So yeah. If there is circular motion, let me say you are disturbing a particle into, by half time it should be going to the other extreme. So half time is this one, by the half time it will be going to the other extreme, by the other half time it will be coming inwards. The other way of saying it is, here it is slightly coming inwards, here it is slightly going outwards. Earlier it was a circular motion, now it is coming slightly inwards, and here it is going slightly outwards, so it is going to look like a ellipse. That should make sense, because Kepler's law says it is going to be elliptical motion. And that's the same thing they were explaining here. Yeah, if you want, you can pause and you can read it. Now, similarly, yeah, we were talking about when in the case of potential energy thing, when n equals to 2, it will be neutral. So you can show the same thing. If potential energy is n equals to 2 format, then it is inversely q force. Now, in this force, you need to show it is going to be, you need to check what will happen. When you do the calculation, you will understand total energy of the particle will be 0. The meaning is when you disturb from one location to other location, it will be stay there itself. I mean, it will be neutral equilibrium. It won't be like coming back or going away. It won't be stable or unstable. It will be neutral equilibrium, right? So essentially what we did is we wrote kinetic energy in terms of, yeah, kinetic energy we expanded and we got three terms. As it is a central force, we can write this kinetic energy in terms of angular momentum, where angular momentum is a constant. So for a given angular momentum, you can convert this entire question as one dimension problem, right? Thank you.